Before 1977, there were no roads in the mountainous region along the Red Sea coast of Saudi Arabia, from Xiaer to the city of Muhail. As far as the eye could see, the landscape was a vast expanse of rugged wilderness, no streams or verdant forests, only dark brown cliffs and sheer precipices rising starkly under the glaring sun. The Saudi government planned to construct a descent highway through the vast mountainous region of Xiaer. This project had to be carried out in a desolate and silent wasteland, scorched by the blazing sun, swept by rolling yellow sands, and devoid of human presence. For the engineers, it was undoubtedly a formidable challenge. The Xiaer Descent Highway is located along the Red Sea coast of the Kingdom of Saudi Arabia and forms part of the Tihama downhill highway system. It extends from Xiaer, 27 kilometers north of Abha, to the outskirts of the city of Muhail. The original planned length was 58 kilometers, later extended to 63 kilometers. The entire route follows the natural terrain and can be clearly divided into two sections. The first 14 kilometers begin at a highland elevation of 1,986 meters, winding down through rugged mountainous terrain and steep cliffside gorges, descending to the valley floor at approximately 1,220 meters within the deeply incised Wadi Teha, an elevation drop of 766 meters. Beyond this point, the road enters a more sharply descending section, continuing downward to its final endpoint at 328 meters above sea level. Altogether, the route experiences a dramatic elevation change of 1,658 meters from start to finish. On October 31, 1977, the Xiaer Engineer Agency signed a contract with the Ministry of Transportation of Saudi Arabia and commenced construction of the Mountain Highway project on December 3 of the same year. Unlike other regions, Saudi Arabia's mountainous terrain is barren, devoid of trees and vegetation. During the early phase of construction, when no access roads were available, the Xiaer Engineer Agency deployed 100 Taiwanese indigenous workers skilled in climbing to join the project. The construction team first used ropes and lightweight drilling equipment to carve out initial foothold platforms on the cliffs. From these platforms, work progressed either upward or downward until it reached the designated roadbed point along the mountainside. During this period, the main task was to build temporary access paths through the valleys for the construction crew. The construction of access roads played a critical role in this project. Full mobilization of personnel and equipment depended on these access routes for coordination and mutual support. The geology of the Xiaer region is complex, and the mountainous area is constantly filled with dust. As a result, the construction of each access road progressed slowly, relying on close coordination between the workers and bulldozers. The entire first year and a half was dedicated solely to building these essential access roads. The first mountainous section of the Xiaer Descent Highway spans 14 kilometers, yet even before main construction began, over 7 kilometers of access roads had already been built. These access roads formed a network of transport routes within the valleys. This highlights the extraordinary amount of manpower and effort devoted to access road construction during the early stages, far beyond what is typically required in standard road engineering projects. The primary access roads were constructed to connect various work points at different elevations. Additionally, individual structures such as bridges and tunnels each required their own dedicated access routes. To avoid excessively steep gradients, the main access roads built along the mountain slopes were designed in a zigzag pattern. The steep slopes and various slope protection measures are defining features of this mountain road's landscape, but they posed significant construction challenges. Achieving the designed roadbed elevation on such steep terrain required continuous excavation and blasting. To carry out the rock cutting, 6 crawler-type drilling machines were deployed, both for stepwise excavation and operation in rugged terrain. In the access road excavation zones, the average cutting depth from the highest point to the road surface ranged from 3 meters to 40 meters, with the deepest reaching up to 90 meters. The volume of earthworks was immense, with total excavation and embankment reaching approximately 2.55 million cubic meters. To maintain the stability of the excavated road surface, several slope protection measures were simultaneously applied to the cut slopes. Rock bolts were used on fractured rock above the excavation line to re-anchor separated rock layers together. Typically arranged in 1 or 2 rows, these rock bolts were generally 3 meters in length and installed using drilling rigs. After installation, the bolts were covered with a layer of wire mesh and then sprayed with a coat of cement mortar. In areas with weaker bedrock, rock anchors were used to stabilize the slopes. This project adopted the Daiwadag anchoring method, utilizing 2 types, Type A and Type B, both consisting of pre-stressed steel bars combined with precast concrete blocks. The pre-stressed steel bars typically had diameters ranging from 26 mm to 32 mm and lengths of approximately 15 meters. A blue grout tube ran alongside each bar for grouting purposes. After the steel bar was positioned and fixed, grout was injected through the tube to secure it inside the rock, enabling the application of pre-stress. At this stage, the bolt at the bar's end was usually tightened only to half of its maximum strength. Type B followed a similar installation process as Type A, but in Type A, the bar length was 10 meters, and the exposed part was a 30 centimeters square concrete block. Each pre-stressed bar could withstand a load of 27 to 40 tons, and after tensioning, the front bolt could be fully tightened. In addition, steel safety nets were installed over the upper slopes above roadside retaining walls in areas with loose rock to prevent falling debris from injuring people. Once slope stabilization was complete, construction crews were able to proceed section by section and continue with the downhill earthworks. Tunnel excavation is one of the more challenging aspects of road construction. For this project, the new Austrian tunneling method was adopted. Depending on the geological conditions, either the full-face excavation method or the top-heading and bench method was used. After blasting, the rock surface underwent 2 rounds of shotcrete application followed by a single layer of lining. The first and second applications involved spraying a thin layer, 5 to 10 centimeters, of cement mortar using a wet mix shotcrete machine, starting from the tunnel crown and working downward layer by layer. This excavation method was designed to minimize rock loosening and deformation to the greatest extent possible. After the first round of shotcrete, holes were drilled into the surrounding rock to install rock bolts, typically 3 meters in length. The installation process involved inserting resin cartridges into the holes. When the steel rod was driven in, it ruptured the cartridges, allowing the resin and hardener inside to mix and rapidly harden within a few minutes. This process secured the steel rod firmly to the surrounding rock. Wire mesh was then attached to the bolts, which were tightened using washers and nuts. A second layer of cement mortar was then sprayed, embedding the bolts and mesh into the tunnel wall to form a strong protective layer. After this second shotcrete application, the rock stress was monitored. If the rock mass was found to be stable, the final concrete lining could then be applied. Tunnels number 13 and 14 are of a relatively unique corridor-type design. The construction method for these tunnels involves first performing open-cut excavation to remove soil and rock, followed by the installation of reinforced concrete lining chambers. Window openings are reserved on the formwork on the side away from the mountain. After completion, the excavated soil and rock are backfilled on the mountainside, while windows are opened on the opposite side to allow better natural lighting inside the tunnel. 3 types of steel formworks are used for lining, 9 meters, 5 meters, and 6 meters in length. These can be disassembled, moved, or assembled as needed. Or curved tunnel sections, the curvature of the formwork can be adjusted during construction. The lining thickness of the tunnel is generally 30 centimeters. The steel girder bridges on tall piers are another distinctive feature of the Xiaer Descent Highway. At every tunnel entrance and cliff edge along this route, towering bridge piers stand majestically, spanning mountains and valleys with an awe-inspiring presence. However, during the engineering design phase by the Italian firm Itaconsult, the company was unable to access the construction site for on-site measurements and had to rely on aerial photographs for design. As a result, the exact positions of the bridge piers could not be accurately determined. When Xiaer Engineering Agency carried out site layout, it was discovered that some of the designed pier locations were suspended mid-air, while others were buried several dozen meters underground. As a consequence, Xiaer Engineering Agency had to conduct design and construction simultaneously during implementation. Due to the mountainous terrain and deep valleys, this road project was particularly difficult to execute. The key to successful bridge construction lay in the excavation of the foundations and the appropriate selection of construction equipment. Most of the construction sites along the Xiaer Descent Highway are located at valley bottoms or cliff edges. The narrow and steep access roads make transportation extremely difficult. At times, concrete mixer trucks even had to be assisted by crawler bulldozers pulling them to complete their tasks, one of the major challenges faced in mountainous construction projects. Moreover, the limited width of the construction access roads significantly hindered the overall progress of the work. The Xiaer Descent Highway includes a total of 20 gradient descent bridges, all constructed in steep mountain valleys. 60% of the bridge piers exceed 30 meters in height, with the tallest, bridge number 20, reaching an impressive 60 meters. To hoist construction materials for the piers and cap beams, 1.5-ton tower cranes were used. All formwork was made of steel. The steel girders were transported to the site in segments by truck and assembled on-site according to the span between piers. This approach helped conserve space at the construction site and eased transportation challenges. For some bridges, where height conditions permitted, 2 cranes were used in tandem to lift and place the steel girders. The Xiaer Descent Highway features a total of 31 gradient descent bridges, spanning a combined length of 3,045 meters. All bridges traverse along the mountainside, with bridges number 6, 7, and 8 forming the most spectacular arc along the route. During the hoisting of the steel girders for bridge number 8, the extreme height of the piers, steep slope, and limited site space made it impossible for cranes to access the area. Instead, a temporary beam hoisting frame was used to lift the girders into place. For bridge number 20, a similar approach was adopted. A temporary beam structure was first assembled on site, and the girders were then hoisted using pulleys and moved into position along the temporary beam. The main construction of the Xiaer Descent Highway was completed in early June 1982. The completed works included road excavation, all bridges and tunnels, 370 box culverts, over 8,000 meters of retaining walls, installation of facade guardrails, and asphalt pavement. Over more than 4 years of effort, Xiaer Engineering Agency's entire team worked tirelessly in this remote and rugged mountain region, overcoming numerous construction challenges with experience and perseverance, ultimately forging this magnificent and majestic thoroughfare. The Xiaer Descent Highway, a world-renowned highway, was recognized by the International Road Federation as a successful example of a unique road engineering project. Since 1966, Xiaer Engineering Agency has ventured overseas to expand its international operations. In 1973, it undertook the construction of the Mecca Al-Hawiyah Highway in Saudi Arabia, which received high praise, leading the Saudi government to entrust Xiaer Engineering Agency with several subsequent projects. Building a grand thoroughfare through the desolate and mountainous region of Xiaer was considered an almost impossible task. Yet, over 40 years ago, Xiaer Engineering Agency, which had come all the way from Taiwan, successfully completed this road on schedule, relying on its wealth of experience, outstanding technical expertise, and the unwavering spirit of perseverance in the face of hardship. Thanks to the unity and dedication of Xiaer Engineering Agency's staff, the Xiaer Descent Highway stands as a testament to their achievement, earning Xiaer Engineering Agency international acclaim. Xiaer Engineering Agency is a source of pride for Taiwan. The resilience, teamwork, and determination demonstrated by its personnel are truly admirable and worthy of emulation.